All right. Hello, everyone. Thank you guys for coming to DAV Lecture 3 on overview of signal processing. If any of you have taken ECE 102 or are currently taking it, this class is kind of like a speed run of basically the latter half of that class and then a little bit of 113. What is that sound?
It just did not look like.
If you keep it pointed here, does it make that sound?
No, that's not true.
Oh no.
Is it related to light?
It appears to be. Okay. Okay, I'll stay on this slide for the time being. Anyway, I'll trim the entire first 3 minutes of this off. But anyway, thank you guys for coming out to DAV Lecture 3 on an overview of signal processing. I will not be moving to the title slide. Anyway, in this lecture we're going to basically be covering a sort of speed run of the core concepts of ECE 102 and 113. And basically we're going to be talking about the fast Fourier Transform, which is a technique that we use in hardware to process audio signals, as well as the intuition behind it, and behind the Fourier Transform and all the little bits leading up to it. So far in DAV we've covered the basics of a digital circuit, so like combinational logic, and gates, binary, things like that. And then last lecture we talked about memory cells and synchronization with clocks. And then we talked a little bit about finite state machines, which are sort of the core foundations of designing a sequential circuit on an FPGA. However, in the real world, we don't use basic input devices such as buttons, switches, and very simple sensors for the vast majority of our sort of information processing. So far, we've been hitting buttons to tell the FPGA what to do, or updating switches. But the real world doesn't really operate on buttons and switches. In the real world, we transmit information in more complicated ways. So for the rest of this lecture, to describe these transmissions of information, we're going to use the term signal, which is essentially, at its very core, a signal is just some information that is being represented in some very specific way. And any process that will interpret or modify or use these signals, it will be called a system. So now, if you've ever been wondering what signals and systems mean as the course title for 102, it's just this. So in this lecture, we're going to be talking about one of the most common types of signals, which is audio. So the goal for this lecture is we're going to establish what exactly we're trying to do with an audio signal. What are the tools that we might need to accomplish this? Why our tools might not work, and then how we're going to make them better so that we can actually process audio information in an efficient manner in hardware. Oh my.
Okay. Audio signals, which is going to be the focus of this lecture. So essentially, all we're trying to do, if you're doing regular DAV, is to take audio signals from a microphone, and then you do something to them, and out in the VGA will be this beautiful histogram of frequencies, which is why it's called digital audio visualizer. So today we'll teach you the foundation of that. What is DAV, or digital audio visualizer? So before we get into that, let's discuss what an audio signal actually is. For those of you who take in 102, you'll know that notes, musical notes, can actually be represented by a frequency. And all frequencies, in fact, have a specific tone that we hear. So here I have a regular C scale and their respective frequencies above it. So in signal processing, we don't get, let's say you play a C chord, C, E, and G. We don't get beautiful split apart frequencies like what's on the left. We actually get what's on the right, which is essentially a sum of the frequencies that we're playing. So does that make sense so far? So our goal today is to take this, which is what we will actually get as information, and return it to each individual frequency that makes up this sum. That's what we're trying to do today. So,
It really
It just doesn't like section headers.
or it really hates well, no. It really hates the composite numbered slides.
alright. So
Or
how you do
non-prime.
that is actually fairly easy. Easy implementation. You brute force it. You try every single one and see what matches up. But how do we do that? We need a rigorous way to see if it matches up. So what does it mean if a signal matches up? So to see if two waves have a matching frequency, all we need to do is multiply them together and take the integral and see if it's non-zero. So for example, we have two waves here, and the first one you can see that there's like a good mix of like the positive and negative ones, so it's gonna be about a 0 for the integral. But then for the perfect match, you can see the integral is definitely non-zero. Does that make sense so far? But unfortunately, this has a flaw, which is if the frequency matches up, but there's a little bit of a shift, then suddenly we still get an integral of 0 with the same frequency. So does that make sense? So how do we deal with that? We test multiple waves and have one that's slightly offset from another. Therefore, if one frequency is just off by a shift, then one of the other ones will catch it and have a non-zero integral. Does that make sense? Turns out these waves is just sine and cosine. So when the cosine is out of phase with the original, then the sine wave should have a non-zero integral and therefore produce a match.
So before we move on, does everyone understand what exactly we're trying to accomplish with this sort of mathematical framework with the sine and cosine? Yes.
Are you adding like the uniform waves to kind of mimic a non-uniform wave?
So basically what we're using the sine and cosine for is we've established that if you multiply a wave by another wave, you kind of get a value that tells you how much the two waves match up in their frequency. So what we're doing is we're multiplying a wave by a cosine, like a pure cosine wave, and by a pure sine wave. And the result will tell us if the original wave matches up with the frequencies of those two waves. And the reason we multiply by both the sine and a cosine is because we want to account for the wave matching up, but also being slightly like out of phase with the sine wave. So if we multiply it by a sine wave and we get an integral of 0, but then we multiply by the cosine and get a positive or negative, basically a large value for the integral, then we're going to know that the frequencies do match up, but it's actually in phase with the cosine and not with the sine. Does that make sense?
Oh, but to answer the first part of your question, yes, we're taking that signal that's like a sum of multiple frequencies, and then we're multiplying it, and so we do this for all the frequencies, and then we see which ones are included in that imperfect signal. That makes sense?
Makes sense.
How precise does this need to be, and like how fast can you do it? Because like, what if your input signals like change?
So we're actually going to talk about that over the entire rest of the lecture. So to answer the question of how precise it needs to be, it entirely depends on like the variety of factors relating to your ability to actually sample and process your signal. But we're going to cover all of that later. As far as like how fast you're able to do it, well, again, we're still talking about it in the theoretical mathematical sense. So we're assuming that you are able to access like the signal at infinite points in time and multiply it by another signal that ranges from negative infinity to infinity, all in an instant basically, and produce an exact value of the the actual multiplication of those two signals. Does that make sense? Basically, we're still in the very hand-wavy theoretical sense right now. Any other questions? All right. So now we're going to talk about actually finding those frequencies. So consider that in the real world, our signals won't look as pure as this one. They're going to look more like that, or something similarly weird and scary. However, if we get a signal like this, we're not actually entirely screwed. Like we have the tools that we need in order to actually process this. And we just need to figure out how we're going to use those tools. So as a famous hockey player once put it, you miss 100% of the frequencies you don't test. So to find the frequencies in the scary wave, like the one that had all sorts of weird spikes and whatnot, we're basically going to try every single frequency and determine which of the frequencies actually match up with our initial wave. And this works because, in principle, when you match the wave using multiplication, it still works even if your original wave is the sum of many waves, as we're going to see in a little bit. So this is an easier example. It's a wave whose frequency components are unknown. And using the power of sines and cosines, we're going to actually extract the individual frequencies just by multiplying this with various different frequency sine and cosines until we find the actual components. So this one specifically, it has two frequency components, and we're going to find what they are right now. So first, we're going to try two waves, a cosine and a sine, each one with a frequency of 1. So as you can see, the integral for both of these multiplications is roughly 0. You can tell just by looking that there's roughly an even amount at the top and the bottom of the x-axis. And therefore, since both of these are 0, we know that f of x does not contain a sinusoid with frequency 1. Does everyone understand how we reach that conclusion? Okay. So then we're going to try with waves with a frequency of 2. So this is our original. And as you can see, when we multiply this by a cosine with frequency 2, the integral is some number greater than 0, which you can tell by the fact that the area under the curve is mostly on top of the x-axis and not below it. And with the sine wave, it's roughly 0. And when we multiply this by a cosine with frequency of 2, we get an integral of 2 pi. When we multiply it by the sine, we get 0. So this tells us that our original wave has a wave component with a frequency of 2. We don't necessarily know how much it is, like how much that wave contributes relative to the others, but we'll figure that out when we go through all of the independent frequencies. And then we're going to try waves with a frequency of 3. So as you can see, cosine sine, frequency of 3. Once again, we have a cosine that matches up, and this time the integral is slightly less than 2 pi. It's actually pi. And the sine is still 0. What this tells us is that our original wave has a wave component with a frequency of 3, and that frequency 3 wave contributes less to the overall signal. So if we combine all of these results together, we get something like this plot that tells us the relationships between the frequency inputs and the actual, like, how much they match. Question?
So if we're comparing our mathematical representations with the original function, when you say original function, what is the actual signal you're receiving?
You will see that in like a second.
Okay.
So basically, to explain this frequency plot, if you've taken 1 or 2, or if you take it, you will see a plot that looks very much like this. All this is telling us is that the wave with frequency 2 contributed more to the overall signal, like the original signal that we started with, compared to the wave with frequency 3. And both of these did contribute, which we can see by the fact that they're, the little arrows are non-zero, but the wave with frequency 2 actually contributed more. And if we actually look at the original equation, this is the plot for it. It's cosine with amplitude 2 and frequency 2, added to a cosine of amplitude 1 with frequency 3. So we can see that the cosine with frequency 2 was actually, in fact, 2 times as much of a contributor to the signal than the cosine with frequency 3. Does that make sense to everyone? Does everyone understand how we use the tools that Claire talked about to actually derive all of this? Question?
What is the computer comparing this representation to the signal that was received? And if it is, when it's comparing, is there already a digital representation of the signal that's being received?
Again, we haven't gotten to the digital representation part yet. We're still in the hand-wavy mathematical, everything exists in infinity to a negative infinity kind of sense. Once we start actually thinking about computers, we will address some of the limitations of actually having to represent a signal in memory. Are there any other questions? All right. So, now that we've talked about all that, we're gonna actually talk about the sort of the mathematical formula that you might see where we actually do all of this, but in a more sort of condensed, mathematical equation type sense. So, first of all, has everyone heard of Euler's formula? Okay, I see some no's, so I'll just quickly explain it. Basically, this right here is Euler's formula. It's a little thing that Euler created, funnily enough, where basically he combines the cosine and the sine wave into one singular expression. So you don't really need to understand the deep intricacies of how this actually works or how it looks, but you should just understand that this expression right here, e to the j times omega times t, is basically the same thing, is equivalent to this. This is our little packed down version of a sine and cosine wave, and this is how we're going to represent that in all of our equations from now on. So omega here is the frequency of the cosines and sines, and t is our time variable basically. When we multiply this by our original equation, it's basically saying that we're multiplying the original equation by a cosine and a sine and doing something with the results. Does that make sense to everyone? Right. So now we're going to put everything together. We're going to take the unknown function, f of t, we're going to multiply it by our packed down sines and cosines, which is e to the j omega t, Euler's formula. And this tells us how much the two signals match when the frequency of our testing sine and cosine is omega. And then we're going to take the integral, because that's what actually computes the area under the curve, which is the value that we use to determine if the two waves do indeed match. Does this part make sense to everyone? Okay. And then, yeah, once you take that entire integral, basically this is the result in terms of frequencies. And this equation is called the Fourier Transform. It's one of the foundational equations in signal processing in ever. Basically, this function takes an input wave frequency, omega, and it outputs a value that indicates how much that frequency contributed to f of t. If it's 0, we know that the original signal probably didn't contain anything from that particular frequency. And as we saw in the earlier plot with the arrows, if the number is higher, that means that particular frequency contributed more to our signal f of t. Has everyone got that? All right.
Oh,
Oh,
So just to make sure, what was f of t again? The actual function?
well, f of t is the initial signal that we're trying to break down into its frequencies. So if you remember when we did the example with the cosine of 2x and cosine of 3x, it was the scary looking wave that had weird spikes everywhere. That's the initial signal. We don't know what its frequencies are. And this is an equation that will basically tell us if that equation has a frequency in it, if that initial signal has that certain specific frequency in it.
I see. So just to make sure, so we're kind of converting from, not converting, we're going from the math to actually, that doesn't make sense.
Basically, the Fourier transform, you'll hear this explained as converting a signal from the time domain to the frequency domain, which is to say that we take a signal whose input is time, basically, and you have its values based on the time t that they occur in, and then we're converting this to a plot where the x-axis, the sort of manipulated variable, is the frequency. So the plot that we get as a result is telling us that if I go back to this. It's telling us that at a particular frequency, 2 or 3, this is how much that frequency contributes to the signal f of t. Does that make sense?
That makes sense.
Yeah. So real quickly to elaborate, because you might not have seen a function that takes in something like j omega as an input, but basically this is just a convention that those electrical engineers use to show that since we're multiplying f of t by the complex sinusoid, which is Euler's formula, our results are now in the complex plane entirely. So you don't really need to worry about this in the rest of DAV because real world signals are real valued, but it's important to actually keep track of the complex values that are represented when you do the math internally, because those affect our final outputs. And when we do the math in hardware, you'll see why this is important. Does this make sense to everyone? All right. And we're going to pause here. Okay, maybe not there, but we'll pause here and take any questions or just give you guys a couple minutes to process.
what's your question?
This might be more of an acoustics theory thing, but how does beat frequencies come into this? Do they just
What does that
get-
mean?
Like,
I'm not a music person.
how does the actual signal versus the sound you detect compare? because, like, say if you generate two very pure sine tones and then you superimpose them, you can hear like other tones, and then when you record it again, it will like ignore the.
Do you hear other tones? I mean, I don't know. I'm not gonna lie. I have no idea about the answer to your question.
Talking about the
There-
harmonic series.
I think it's mostly just, let's say you're playing it forward, is that what you're talking about, where it's just like, it's not three pure tones, but maybe it's like a transition, is that what you're talking about?
No, you just like if you generate two frequencies and then you play them together, like physics reasons, there's like you hear other stuff. So then when you decompose that, does it just ignore the other stuff, or does it like, only capture the pure?
Well, if you're playing two pure tones, then the resulting frequency, as we said, will be a sum of them.
Yeah.
And then when you're testing one frequency, yeah, you ignore everything else in the meantime.
So if you test like this mystery frequency that gets, so say the sum of them or whatever the physics is, I'm not sure, will it still be detected or not?
Okay, I think I understand the question actually. I think if what you're saying is correct, that due to reasons of physics, when you add two tones, you actually get like some sort of interference, which is definitely something that happens. When we do the Fourier transform and actually like try to decompose the resulting signal, we will get the other like components that have frequencies that aren't the original two. The Fourier transform will take a signal and extract any and all frequencies that are present in it, even if some of those frequencies are like not what we intended for, in order for, like not what we intended to actually be there.
I assume there's ways to tell which ones are real and which ones are fake. Or-
Yes, there is. That's not something that we're gonna get into, but like filtering out noise from a signal is a fairly active area of research and study.
Any other questions? Okay, should we move on?
Sure. Doesn't mean that we need to show you guys that we found
Oh,
while
yeah.
making this lecture.
Please enjoy.
That's it.
Yo.
Yeah, that's it. Okay,
Yo.
I'm gonna skip that one just in case. Okay, sampling time, as I said. Yeah, this section will tell you how we take a real world signal and put it on our digital hardware. Because the main problem is when we have a real world signal, there's, as Frank said earlier, we're testing like negative infinity to infinity. But our FPGAs don't have infinite space. So we can't actually store a perfect signal. So what can we do? The result is we will sample, which means at some specific frequency, we're going to look at the value of the signal and then take it out. So therefore, when we pull at every point like this, you can see the white dots is our samples. Then we get something that looks like this. So it's not a pure line from one point to another, but now we have a discrete signal, not a continuous one. And by doing this, we're able to take our previously infinite signal and condense it down to a series of points that we can use. Does that make sense? Okay. So just to reiterate,
No.
okay, just to reiterate what that slide was saying is we want discrete signals because it's more digital friendly, doesn't take up infinite space. Because continuous signals, while they're perfect and will give us like the perfect data, we can't store all that information. That's all. And so, how do we know how fast or how slow to sample? There's actually a rule for that, but here's what happens if you don't sample it at a correct frequency. You'll see on the right, on the left, sorry, that we sample at a higher rate, which means we take more samples per period of time than the right side, right? So on the left we have more points than the right. On the left side, we can kind of see the original signal, right? But on the left side, actually, it's results in a lower frequency. We lose too much information, and we can't regain what the original signal looks like. So there is a rule for that called the Nyquist rate, which basically says, as I said before, we need to sample fast enough to get enough points to the point where that we can recreate the original signal. And the magical Nyquist rate is 2 times the maximum frequency component of the original signal. And as I said earlier, if you sample too slow, then you lose too much data, and it restricts the range of frequencies we can actually detect from a signal. Does that make sense? Okay, now it's your turn. Here's the same C scale from before. What's the minimum sampling rate to extract all of these frequencies?
1026 or 1046. Sorry. 1046 hertz.
Yes, that is. Thank you for participating.
All right. So now that we've talked about the mathematical framework and we've established why it won't work anymore, we need to basically make some changes in order to actually use this with a sampled signal, which as we discussed, will not have the entire range of negative infinity to infinity, and now our input frequency is in hertz rather than some nebulous concept of a complex number. So we're going to address each of these individually. Since we don't have continuous samples, we can't integrate because, for the time in between 2 samples, we can't really calculate the area under the curve. So instead of integrating, we're just going to use the discrete version of that, which is the summation. We're going to use the giant sigma instead of the giant S. And then, since we're restricted to a specific time interval, which is just the number of based on the number of samples that we've stored, we're also going to restrict the summation bounds. So as we see here, now instead of the integral from negative infinity to infinity, we have this summation from 0, which is our first sample, to capital N minus 1, which is our last sample. And of course, the samples that we store, now the sort of concept of time is abstracted away because it's all based on how many samples do we have and what is our sampling rate. You can recover the information that you need to just using this bit of information. And then also, as you see here, we no longer use time as our input to the function. We just use N for that for the sample that we're trying to extract. And similarly, we replace time over here with N over the maximum number of samples, capital N. This is not our final equation. We have one more change we need to make. So, real quick, the N over N here, this is a byproduct of the fact that we're doing a discrete Fourier transform now. So basically, what this means is that as a result of using a bunch of discrete samples as opposed to an entire signal from negative infinity to infinity, our Fourier transform is no longer as accurate. Which, if you think about it, it makes sense. If you lose information in the signal, you lose information in the output. So in the DFT, what we actually do is we don't produce a frequency, or we don't produce the little arrow for one particular point in your time space or your frequency space. Instead, what we do is we subdivide the range of frequencies into bins, such as these ones that you can see here. So the capital N is not really based on the number of samples as much as it's based on the number of bins that we're trying to subdivide. And we produce the magnitude for each range, and as a result that we get a histogram that looks more like this. So if you've seen the final digital audio visualizer, you've seen that there's a histogram on it. That's actually this right here. So what we're doing here is this is an 8-point DFT, and we're saying that each of these bins represents 1/8 of the frequencies going up to the sampling rate. So the frequencies in this bar right here contribute more to the overall signal. So the frequencies in this bar right here, they contribute more to the overall signal than some of these other bins, but we don't know what the specific frequency is. We just know that it's somewhere in that range from, say, 1/8 of this, from 2/8 of the sampling rate to 3/8. Does that make sense so far? So now we're going to go back to the equation. We have one more change we need to make. Since we're working with real digital signals, it doesn't make sense to think in terms of the j omega, which was something we used for the really hand-wavy mathematical stuff. So what we're going to do is we're going to take the j out of our parameter to this Fourier transform here, and we're just going to replace j omega with k, which is going to be an input frequency in hertz. Because in the real world, we represent frequencies in terms of hertz rather than radians per second. So in order to do this, we also have to convert it from radians per second to hertz, which is why we multiply by 2 pi over here. And by doing all of this, we get this equation right here, which is the discrete Fourier transform. This is probably one of the first things you learn in UC 113, I think. And like, you'll learn about this and also how to use it in a more sort of hardware sense, which we'll talk about in a little bit.
Oh, wait, question?
Is K some standard, or like why is it not F?
I have no idea. K was what was used in the Google images for equations that we looked at when making this lecture. But yeah, K is.
Also, yeah, there's lots of other F's in there.
That's probably it. Yeah, they didn't want to use F. F of F is equal to summation of F of n times. Yeah, you get the idea. Any other questions? For IT. We're gonna pause again for more questions, but this time. Oh, yeah, we also need to show you another meme to keep you entertained.
Any other questions?
Cool. I'm glad we could keep you guys entertained. There's also this.
Oh yeah, these are my memes.
Yeah, could I make a loot table for me for some reason? I don't know what's up with that one.
I made a loot table for everyone. That's yours, and I think.
Yeah, yeah. Apparently I have a 1 in 3 chance of dropping a sus or an amogus. What was this supposed to represent again? Just 1 in 3 chance of saying sus when I die?
Perhaps, but more importantly, you drop like a expensive ass.
I drop an FPGA 1 in 4 times that I die, so
It's a higher chance.
if you guys were thinking of making a mob farm with me, you guys
Yo.
can be
Mob
serious.
farm
Yeah,
is crazy. That's actually pretty. That's actually a crazy.
Oh, and then the
idea.
top 2 are guaranteed.
Enderman
Oh,
farm for
bongos and cereal.
Enderman farm.
Anyways.
I'm just saying, it's hard.
It would, because I also drop I also have a 1 in 10 chance of dropping a yike bill.
Singular
Just-
like.
Yeah.
Yeah, singular yike, basically.
Yike.
Anyway, back to lecture. So, now we're going to talk about now we're going to talk about how we actually do this in hardware with the fast Fourier transform. So basically, to explain why we need a fast Fourier transform, we have, in order to compute the discrete Fourier transform, we have to multiply each sample by Euler's formula, and then we have to sum all of them up. So this is like n multiplications and then n minus 1 like additions, and that's a lot of, basically it's a lot. For you CS nerds out there, this is a time complexity of O of n squared, which is bad. So we need to find a better way to do this, and in fact, some math heads in the 1900s actually did. So basically what they did is they designed this wacky diagram over here, which basically shows us sort of a, I guess, diagram for how we can reuse the multiplications in the DFT a bunch of different ways to reduce the number of multiplications that we have to do. This method of computing the Fourier transform is in fact very fast, and therefore they decided to call it the fast Fourier transform. It is crazy, I am aware. But why does this work? We're going to figure that out now. So, we know that computing the DFT for a lot of points takes a long time. Like, it takes n squared for n points, n squared computations. But when we have very few points, it is basically trivial. So for example, when we have exactly 1 point in our signal, which doesn't really make sense, but just follow along for a little bit. When we have 1 point in our signal, the DFT is literally just the value itself. So computing the DFT is trivial now, and this is really good. So what we want to do here is we want to actually break down the problem of the DFT into a bunch of 1 point DFTs, and then sort of compose them all back together. So we're gonna now try to figure out how we're gonna do that. So intuitively, if you take a 2 point discrete signal, such as the one right here, you can see that we can sort of decompose this into 2 1 point signals by taking like each individual point and then shifting one over. So as you can see here, we have 2 individual 1 point signals where at t equals 0, the point is just like the value of f of 0 or f of 1. And if we shift one of them over and add them together, we get this signal right here, the 2 point signal. So in order to shift a signal in time, we multiply its frequencies by a complex sinusoid. We're not going to get into why that works really, but this is a property called modulation, and if you take 102, you will get into the weeds of it. Does everyone understand what we're doing with the 1 point signals to make the 2 point signal? This is really important. All right. So, hello. Bro, what?
That's the end of the presentation.
really hope it isn't. Alright, anyway. So, now we're going to look at the actual math for this. We see up here we have the DFT equation for 2 points. And if we break this down into the actual like summation, if we like expand it, we can see that we have multiplication by this and multiplication by that, which is the same thing since this is going to be 1 because that's 0, therefore this entire term becomes 1. This f of 0 stays f of 0. And then this is going to be multiplied by that, which is multiplying f of 1 by a complex sinusoid. So as you can see, what we're doing in the DFT, where we multiply the point by a complex sinusoid, that's basically a modulation. We're shifting that point in time. Does this make sense to everyone? How we got from the original equation to understanding that this is basically the modulation that we talked about in the previous slide. Okay, so now if we look at the 4-point DFT, we can similarly break this entire giant equation down into 2 signals, one of which is modulated. Can you guys see how? It's okay if you can't because we have it on the next slide. This is not an interactive thing. It's kind of hard to figure that out instantly. Basically, if we take a 4-point signal and we dissect it in the same way as we did the 2-point signal, it kind of becomes clear how we're doing this. We're taking 2 2-point signals, shifting one of them in time by 1 time step, and then we add them together and we get the 4-point signal. So now if we sort of reverse this process with the mathematical equation, we can see that we have f of 0 and f of 2 are kind of one group. And then this is the time shift, and then this is f of 1 and f of 3, the other group. And we're shifting it by 1 time step. Does this make sense to everyone? If not, we can always review this. We have plenty of time. Sure. So, you see how here we have an initial signal composed of f of 0 and then f of 2, which is shifted over by some amount. That is corresponding to this yellow right here, where we have f of 0 and then f of 2 is shifted over by some amount. Does that part make sense? And then in this next group, we have f of 1 and then f of 3, which is shifted over by some amount. That's this right here, the y signal, which we had to give them numbers for the sake of like mathematical rigor, but in reality, you should pay attention to the fact that these are basically just the 2 individual parts of the original signal. We're taking these points and we're shifting them over by 1 time step as given by this term right here, which is a modulation over by 1 time step. Does that part make sense? Yeah, so now basically what we have here is we have the original signal, which is the yellow. We have another part of the original signal, which is blue. And then we shift the blue part over by 1 time step to get this. And then we add them together. We combine the 2 into the original f of t. So as you can see, f of t is in fact equal to splitting all of it like that, which in terms of the actual like diagram is equivalent to just we're just decomposing it into 2 different 2-point signals. Does that make sense?
So just to make sure, is the whole point of these to kind of separate the 4-point signal into 2 separate signals with 2 points each?
Mm-hmm. Yeah, so basically, as we talked about earlier, the DFT of a 1 or 2-point signal is really easy to compute. It's like almost instantaneous. So basically, when we have a real world signal that's probably going to be like, I don't know, 16, 32, even like thousands of points maybe. What we want to do to compute the Fourier transform of this is we're going to slowly split it into 2 signals, each one being half the length of the original, and then we're going to split that into 2, split that all the way down until we get a bunch of really small signals. And then we can compute the DFT of those and then sort of compose them all back together, and that will get us the f of t without having to do the crazy amount of math that comes with doing the DFT on a large signal. It's kind of like, if you're familiar with the divide and conquer paradigm, that's basically what the FFT is. We're dividing the signal into a bunch of smaller signals, conquering each one, and then composing them back together. Justin?
Is this the reason why, like, if you try to do, like, an FFT in, like, Python or something with, like, the NumPy library, like, it requires that you put in, like, some power to like run like.
Yeah, probably.
Okay.
I'm actually not sure if it even does require a power of 2. Like I feel like I've used that function without a power of 2 samples before, but like that's probably it. Right.
In this case, would the complexity of this be L of n all raised to 1?
Yeah.
Okay.
Yeah, that's the complexity of the FFT. But yeah, so any other questions?
Oh no, I was just asking if you could stay on this slide for like
Oh,
a second.
yeah, sure.
The last one. Yeah.
This one?
Yeah. Wait, no, sorry. It's like the one with yeah, this one.
Okay.
How are you doing that? Your computer's about to die.
Is it really?
Well, that's why the clicker stopped working earlier. So.
Ah, I see. Well, my charger's in my backpack if you wanna.
Where is it?
Alright, can you pause the recording while we're
You can just like splice
This
it
is a
together.
we're good? Cool.
Yeah.
Anyway, so now basically we've talked about how we actually divide and conquer our 4-point signal into a bunch of 2-point signals, and then you would do the same exact thing to decompose the 2-point signals into a 1-point signal. Hello. Again. Cool. Anyway, so yeah, this is just kind of quickly recap what we just talked about. This part that we just saw in our equation, this is the 2-point DFT, but with f of 0 and f of 2 as our initial signal. So essentially, the 4-point DFT is a bunch of 2-point DFTs, and each of them is a bunch of 1-point DFTs. And with that, this is a divide and conquer algorithm for the DFT, which is the fast Fourier transform.
So we showed this diagram earlier, but now that Frank has explained what the fast Fourier transform is, let's look at this again. So we demonstrated on a 4-point FFT. That is what this diagram is. We have our 4 points of 0, 1, 2, and 3. And the reason why they're ordered by this, oh yeah, you switch to, not used to it. Okay, 0, 1, 2, and 3. The reason why they're ordered like this is because of that divide and conquer. So remember how we grouped 0 and 2 first? And you'll see that that's why they're next to each other like this. And then 1 and 3 are similarly grouped together. Now these two are put through our 2-point fast Fourier transform. And the result you can kind of think is like this plus minus, those are the results of our fast Fourier transform. We'll get into that a little bit later. But then the next step is we take the results from this first one and then combine it down here. So that's what the diagram's representing. We're taking F0 and F1 as our second stage, and it's still a 2-point FFT. So that's how we're able to combine them and eventually end up with our 4 values on the other side. I see some confusion. This is a lot, so I believe we get into it later on. So I showed that there are these plus and minus signs here. I told you that those are the results. Well, what does that actually mean? This is a handy thing that the fast Fourier transform does, which is it increases symmetry by noticing that when we shift the e's halfway around the circle, we just get a negative of the same value. So therefore, if we go back one, that's why we just negate it here, and we can reduce the complexity by just doing the same thing and then negating the outcome. That make sense? Okay. So let's look at each individual component really quickly. This is a 2-point DFT that we just talked about, I guess FT. And let's look at the components. We have our input signals, F0 and F2, right? So we multiply them by this mystery number that we'll get into in a little bit. But then we take F0 plus F2 with this time shift. You can take this as a time shift now. And then F0 minus F2 with this time shift. Does that make sense so far? So this is the 2-point, remember the diagram that we showed earlier, the 2-point FFT. This is, okay, we're taking this one value and then shifting the next one, and then we're summing them together, but this one is negative because of that symmetry that we just discussed. Is that clear to everyone so far? Alright, let's get into what this is W. So we are applying Euler's formula to multiply this whole thing by sine and cosine. And here we just actually have this notation called W. It's called a twiddle factor. But what is it in this case? We can look at our unit circle from before. So for a 4-point FFT, we can divide this circle into 4 points symmetrically and then take the coordinates. So if it was an 8-point FFT, for example, we'd have like an extra point here, another one here, here, and there. Does that make sense? And so for an n-point FFT, we're going to divide this circle by n, and then we're going to take the coordinates. That make sense so far? Okay, so let's get into the notation. So we called this a time shift earlier. You'll notice that it is our like our sines and cosines through Euler's formula, and through Euler's we're going to expand it into this longer form. So you see here's our cosine and our sine, and we have the 2 pi times our hertz that we mentioned before to turn into frequency, and then n is the like n-point FFT. So you'll notice that for, we have a k up here and n. So n, as we said, is the how many points in FFT, and then k is like what stage are we sampling? So a little bit to this one. Oh, that's a long way. Yeah. So you'll notice that in here we have our k, this is the 0, and then the n is for this whole thing. All right, so now that we've gone over that, who wants to take a crack at 2-point FFT for these 2 signals?
You'd basically be doing what we did in the other slide where we showed the equations for this particular, the particular like blue cross multiplication thingy. You just explain to us what the equations are.
So you take the value of F1
Mhm.
and add to it the value of F3 multiplied by the twiddle factor,
Mhm.
and then you take like how the value of F1 minus F3 times the twiddle.
Yep. Exactly that. So we have F1 plus, here's our twiddle factor, and then F3. So here's k, here's n, and then F1 minus our twiddle factor times F3. Exactly right. If you were confused. Okay. So now that we've gone over these 2 individual components, what's next? It's just a matter of scaling up. So as we said before, this is a version of dividing and conquering. So now that we've done these 2, we can take the results and put them into another 2-point FFT to get a final result. And actually, you can continue scaling this up as long as you have the right twiddle factors, and you keep scaling it up. This is what DAV is. Yeah, this is DAV's final product right here. So we've essentially taught you how to get, well, kind of, how to get to
Go more, not distract it, but like.
This is true.
But before we move on, is there any questions as to how we got to the 2-point FFT and then the 4-point, and then beyond is for you to figure out later. But
Or just any questions about the diagram or anything else, because it's a lot. We get that. We struggled a lot with this last year as well.
Could you go over how to calculate that like cross diagram?
yes.
How to calculate it or how to like derive it? The calculation is what Alex said, where you just like multiply and add. Oh.
The derivation.
Okay. Third, you wanted?
Yeah, let me find the slide for that. Okay, so,
It's gonna be the previous section, right?
oh, right, I'm going ahead. Okay, so I think it starts. Okay, well, do you understand how we got to the derivation of the 2-point? Okay, so looking at this diagram, you can think of each of these classes as 2-point FFT. So you're taking 1 point, and then you have your shift, and then you add them or subtract them. Does that make sense so far?
Yeah.
How to get to that? Okay. And then, are you talking about like the next layer, or just this?
That's the small one.
Okay. So, is it like the total factor thing you don't get, or just the connection of the items?
Just the connection.
Oh, okay. So, I think this diagram will show it better. Right here. This is exactly what's in this diagram. So let's go back here and look at it. So you see that these two, we're actually able to take out this similar time shift from 1 and 3, right?
Mm-hmm.
So we can break it down into two 2-point FFTs by recognizing that, okay, we just have one that's like a little shifted here. And so what that means is for this first one, we break it down into, okay, we have our first point here. And then we have that time shift here, as we were before, with the second one. And then this is just the same thing, right? This is the same thing as this top one, but just with this extra time shift. So that's why it's paired like F0, F2, F1, F3. Alright, so any other questions so far?
But can you go back to like the diagram? So like with like the two blue ones, are there two different ways to calculate F0?
What do you mean?
Which F0? The small F or the large F?
Wait, so like the two on the left side are for the small F0, and then like the two on the right side are for like the large F0?
Oh, no. Basically,
Here.
what's going on here is we're saying that this entire diagram is like a system that we'll plug in our individual samples into. So in order to compute f of 0, we're going to first do the FFT, the 2-point FFT with these two, get like sort of a like I guess an intermediate stage values right here. So we're going to compute these, and then this is the value that we actually care about at this point. And then we're going to also do the bottom two, get this value, and then to compute f0, like the frequency bin value for the 0th bin specifically, we're going to now multiply this one by the total factor and add it to this one.
Okay.
So this is like an intermediary stage where the values are computed by doing these like butterfly calculations, and then if we go all the way through, you'll get these actual bin values. And if you like plug in a value for like a if you plug in the frequency bin that you want and like work through the equation, you might be able to see how you get this particular operation. This is just reusing the multiplications that we do for each and every individual DFT. We're just reusing a bunch of them so we can kind of condense it all down into one.
Just to elaborate a tiny bit, the intermediate stages are the values we showed before, which is like F1 plus F3 times total factor, or F1 plus minus F3 times total factor. That is what goes into this next stage. And Prane mentioned butterflies. That's just what we use to refer to the 2-point FFTs because they kind of look like butterflies.
Yeah. Well, I was just gonna ask, can you scroll back to the previous slide real fast? Oh wait, sorry, the one with the the intermediate calculations. Yeah.
I'm not sure if you went over this already, but in the diagram you have the minus, right? What is the minus?
Yeah, so basically the idea behind using the subtraction instead of addition is if you look at some of these signals, they're modulated by e to the power of negative j times something times 1/2. And if we look at a unit circle right here, you can see that if you move halfway around the unit circle, you just get the negative of whatever this value is. So basically what we're doing in the diagram is we're actually saying this is adding like this with f2 times this, and then this is going to be adding f0 with f2 times w2 4. if that makes sense. But W24 is just like the negative of W04, so we can reuse that multiplication as well. Does that make sense?
Yes.
Okay. Any other questions?
These are good questions. Thank you for asking them. Okay, so we've told you all of this stuff, but we're going to release a lab, and how do you do it? How do you turn this into code? Well, this section will be all about that. So remember how we talked about how everything is on a complex way? That means that we will need to do complex math. And for our purposes, we have this hopefully familiar form of a complex number where A is real and then B is the imaginary component. Good so far? Okay. So just as a refresher for how you multiply two complex numbers, because we will be receiving complex signals, is you have, okay.
Oh.
I think that
Should be a plus
Yeah.
sign. Yeah, okay.
It's okay. So
We'll fix that
multiply
before we release the slides.
the real one and then multiply the imaginary ones and subtract it, which just turns into -1. And then you add it with, this is the imaginary part now, and then real part here, imaginary part here, real part here, and then real part here, imaginary part here. It's foiling, and since, A times A equals -1, then we can just subtract the product. So this actually turns into, again, like the A plus GB form, which is, this is our new A, or our real component, and this is our new B, or our imaginary component. Does that make sense? Alright, so if we multiply it like that, we get a much longer product. We're dealing with bits now, and let's say our reference input is we receive 32 bits. And 32 bits, I think the first 16 will be real, for example, and the second 16 will be imaginary. So that means that we're taking a total factor of 16 bits so we can multiply it, and then we get this way too long product, because we still need to add it with our real one, right? And so if we go back to here, okay, we can see that we have our real component and our imaginary component. You can think of it like that. Alright, so this doesn't work. What now? Well, the solution is, I don't want to call it stupid, but essentially all we're doing is we are going to concatenate, in a way, our result of our multiplication. First of all, we don't need the sign, so you can toss that. But since we need to add or subtract it with our real number, which is 16 bits, we still need to discard the last 15 bits. But that just means our number is wrong. Spoiler alert. Because by dropping these 15 bits, we're essentially right-shifting it, or making it smaller, by 2 to 15. So now our answer is wrong. So in order to account for that, you shift your twiddle factor by 15 bits, or multiply by 2 to 15, to cancel out this division later on. Does that make sense? And so after you do that, you're able to add or subtract your result with your already real A and get the result. So I've divided this diagram up, I forget if I talked about it later, into the real side, because remember we get a 32-bit number which has like real and imaginary, 16 bits each. And our total factor will also be real and imaginary. So you'll have two calculations to do here. On one side is the real side and the other is imaginary, but you can just think of them as just a 16-bit number. So we have our W times our B here, as said before. I'll get to in a little bit, which is too long, so we need to chop it, and then you can add it to the A on each side. Alright, what's your question?
I have two. So
Yes.
first, in the original numbers,
Mhm.
where does the sign bit go? 16 go to the real component, 16 for the imaginary. And
Well-
second,
Each
Yeah.
of the real and imaginary components have a sign bit.
Okay.
You can think of it as like, we're basically taking the real component, which is a separate number,
Yeah.
and the imaginary component, which is a separate number,
Yeah.
and we're just sticking them together for the purposes of representing this in hardware.
Okay. And does the 16 bits itself include the sign bit, or do we
Yes.
just insert? Okay. And then the second question is just, does the sign bit like only count for the sign, or is it actually like a weighted? Like,
Sorry.
which convention is it? Is it like 2's complement, or?
It's 2's complement. We're going to be doing everything in 2's complement.
Okay.
Is it a plus minus?
Yeah, because remember how in our total factors we have one side that's plus and one that's minus?
Okay.
And then I think at the end, I don't show this, but we need to stick it back together.
Yeah. So I guess
the
more
plus-
accurately, it would be A plus or minus B times W, and not B times W plus or minus A. But yeah.
But this is like an example of like maybe the steps we'll take to get.
What is the MSB of the second of the last line represent?
This,
Yeah.
that's the sign bit of, basically, when you do signed multiplication with two signed numbers, in the result you're going to have two signed bits, because that's just how it kind of plays out. Like if you have, say, I don't know, 8 times 8, but like, since it's, if you have like two 4-bit numbers, -8 times -8, so that would be 1000 times 1000. If you do the multiplication, you're gonna get positive 64, which would be like, I can't really do this in my head, but as far as binary goes, maybe just trust us on this one. We'll show you the math at some other point when we have, I don't know, time and space.
Any other questions? This is what will be in the next lab, so please make sure you understand this. What's up?
Should that purple thing,
Mhm.
like, it says real result, should that be imaginary?
That should be imaginary.
Oh, yeah. It should be
Bruh.
imaginary. Copy and paste moments, yes. Okay. any
As you
other-
can see, when we're 80 slides into a presentation, our proofreading skills go out the window.
What's up?
When you say like real W, like 15, that's a left shift.
That's a left shift.
Okay, so you are left shifting.
Yes,
Yeah.
because here we are right shifting, and so we want to cancel that out by left shifting here.
Oh,
The idea is basically, in order to actually represent, like take the 32-bit number that we got as a result and put it in 16 bits, we have to chop off 16 bits somewhere. We do one of the sign bits, and then 15 bits need to come off the end, because that's how we keep it accurate, so to speak. But then in order to have this actually represent the correct amount and not just be an incorrect result now, we have to undo the division by 2 to the 15 by actually left shifting by 15 with the original number. Yeah.
Any more questions? No? Okay, just to recap what we've done today. A lot of this, as you saw on that huge diagram, is a lot of wiring. Each time there's like a line to a section, you're just saying, oh, I'm gonna direct this input here. It gets complex really fast. So make sure you follow the diagram as best as you can. And if you're stuck on what twiddle factors to use, the unit circle is a great way of calculating it. If you keep the first half real, second half imaginary convention throughout, it makes it a lot easier to pass complex numbers from like stage to stage. So that's why we asked you to do it like that. Next, we're going to say multiply B times W with the truncation. Remember how we said we need to shift, left shift W, so make sure you're doing that. And then finally, our output results will be something like this, where A is our real number, and then we have our B times W, which is our imaginary. And that is what either goes on to the next stage or is your result. And congrats, that is what a butterfly unit is made of. This is a butterfly unit. And now you can make as many FFTs as you want.
Yay.
Do you have a scientific explanation for why that happened?
No, actually. Do you want to find out?
then I can structure like you need to like an article. But there's the integer, right?
Yeah.
How the fuck would like integer structure? That's what I'm thinking.
Oh.